aka EDA, exploratory data analysis. All right, I promise to never do that again. Hello, my beautiful coding cuties. How are you doing on this fine day? You can't answer that, so I'm really not sure why I asked. You can comment, I guess. Anyways, you're watching Damsel in Data. Welcome back. This video is meant to show you the steps that you need to take in order to get a project on your resume before you start applying to data science roles. So I'll be sharing my general framework that I follow, as well as some tips that might be good to know as you're working through your project. All of the resources and websites and everything that I mentioned, I'll be linking in the description below. Before you watch this video, just want to make sure that you have a basic understanding of data science terminology, and I will just leave it here and you can come back to it if you need a glossary at any point of the video. And finally, you will need familiarity with Python or a similar language like R. So without further ado, let's dive in. First things first, before we start building our project, how do we decide on a project? You should pick something that's interesting for you to work on. This will help keep you motivated and excited to work on the project. Aside from that, I do get asked a lot, what's a good project to start with? You can't find something that's interesting to you if you don't know what the options are. Fear not, my friends. Kaggle.com is the answer. Please sponsor me, Kaggle. Kaggle.com is a great place to find both problems and data sets to solve them with. And you can also see the solutions that other data scientists have submitted, including their code. So it's really a great place to get started and to learn how to solve these problems. You can browse through the data sets, check out the popular ones, and pick one that has a lot of submissions so you can have support as you're working through the project, and also one, again, that looks interesting to you so that you could put your heart and soul into it. The classic beginner data science project to work on is the Titanic classifier. The idea is to build a classification model to identify which passengers will survive and which ones will not survive. So it's a really fun project, lots of support, nice clean data set, and a great project to start with. If this is not your first rodeo and you would like a more challenging problem to solve, I'll leave some links in the description to help inspire you to pick your own project to work on. Step 0, I guess, part B is data retrieval. You need data in order to build a machine learning model or any kind of data science project. How much data is required exactly? This is a great question that does not have a clear-cut answer. It depends on your data set and the problem that you're trying to solve. But you need at least 1,000 data points, at the very, very least. And it's better to have tens or hundreds of thousands for most problems. There are many ways to retrieve data. This can be as simple as clicking a download button if you're using a resource like Kaggle.com, or you can scrape your own data from the web, APIs, etc. The choice is yours. All right, so step 1.
Exploratory data analysis.
Once we have our data, we need to understand it. The way that we understand our data is through exploratory data analysis. The goal of this step is to take note of the processing steps that we will need to take in order to prepare the data to be fed into a machine learning model. Understanding what the data looks like will also help us decide which algorithms to consider for our machine learning model. Now, what I see a lot of people doing with this step is creating all kinds of beautiful plots and visualizations that describe the data, but then they don't really do anything with this information. So they're creating all these plots, but they don't really know why they're creating the plots because they do the analysis and then they just go straight to the processing, and it's kind of like the analysis was just done for fun. I wanted to leave you with some questions that you can aim to answer using your EDA. Do we have a data dictionary or metadata to explain to us what each of the variables mean? If not, do we understand what each of the variables mean? What are the data types that we're working with? Are we working with integers, strings? Do we have categorical or continuous values, or maybe a mix of both? And how do we plan on processing values that are non-numerical? Do we have missing data? Do we have outliers? Do we have unexpected values that we're going to need to clean up? Now is the time to take note of all of these things so that we can deal with them in step 2, which is data processing and cleaning. This step will probably take up the majority of your time. If the data is anything close to real world data, it will be dirty, honey, let me tell you. I've broken down this step into 4 types of data processing and cleaning that typically need to be done. And they don't always all have to be done. It depends on your data set and your problem, but you should do a check for each of these 4 steps and consider if they're relevant for the problem that you're trying to solve. First step, drop or process values that are missing, unexpected, or potential outliers. If we have a data field called month and we have months in it like January, February, March, April, and then we see something like Tuesday, that is not a month and that's an unexpected value, we need to process that. So either drop it, fix it if we know what it should be. The second part of data processing is to convert your categorical or non-numerical variables to numerical variables. This is because machine learning algorithms cannot understand values like January and February. They can only understand numbers. So every single piece of data that's going into your machine learning model needs to be a number. And it's important to understand the math behind the way that the algorithms work, because you can convert the non-numerical values to numerical values in different ways depending on the algorithm that you choose. Typically, a good rule of thumb is label encoding for ordinal values and one-hot encoding for non-ordinal values. An ordinal value would be a categorical variable that has some kind of inherent order. In the months example, we have January, February, March. January comes before February, which comes before March. So there is a natural order associated with these values. A non-ordinal variable would be something like a color. So colors can be like red, orange, blue. There is no inherent order in these values, so this is a non-ordinal variable. For ordinal variables, you would choose label encoding, and for non-ordinal variables, most of the time you could choose one-hot encoding or creating dummy variables or indicator variables. All right, next, step 3, determine which, if any, additional data processing steps are required depending on the model that we will be choosing down the line and depending on what your data looks like now. Some additional types of processing that you can do are standardization, normalization, dimensionality reduction, or feature engineering. And I won't go too far into what each of these 4 things are. I won't go into it at all, actually. For the sake of keeping this video lean and mean, there's tons of resources online, which I will leave for you in the description. But if you would like me to make a video explaining any data science concepts like these in the future, please let me know in the comments. I'm happy to do that. So now, finally, the 4th step of data processing is splitting our data. You will do this no matter which algorithm you choose, so finally something that's not wishy-washy. So first we need to split it into X and Y, and next we need to do our train test split. The X and Y split is removing the dependent variable from the independent variables. The dependent variable is our Y, it's our target or our label, what we're trying to predict, and then the independent variables are all of our features that we're using to make the prediction. Next, we need to do our train test split. I typically like to do a 3-way split into train, validation, and test. Our training set will be used to train the model. The validation set will be used to optimize the model. So here we're going to test how well our model is doing after each iteration of changing something in it. And then finally, our test set, we're going to leave it until the very end when our model is complete, and that test set will give us a true picture of how well our model will perform on unseen data. Some good numbers for this split are 70% for training, 20% for validation, and then 10% for testing. All right, moving on to step 3. Now that all of that stuff is out of the way, we can finally get to modeling. Woo! We have to choose an algorithm. There are so many algorithms to choose from. So this is where it's important to go back to that lovely machine learning theory that you learned, review it, understand the models, how they work, when to use each one, so that you have a narrowed down selection to choose from for your particular problem. There's an expression in the world of machine learning and in the actual worlds of other things. There is no free lunch. What this means is that there isn't one single machine learning model that can solve every single problem every single time. There is no such thing except XGBoost. I'm just kidding. There is no free lunch, really. No model will work for every problem. Now, that being said, some models are definitely more robust than others. XGBoost. But the best algorithm will depend largely on the size of your data, the shape of your data. Is it categorical? Is it numerical? Is it mixed? What are the relationships between your variables? And also, do you have any specific business goals? Like, for example, everyone loves deep learning and neural networks, the most sexy machine learning models that are talked about by everyone. However, these models are typically a black box, which means they will give us an answer, but we may not understand exactly how it got to that answer. And some data science business problems would demand an explanation for why you came up with that answer. Here are some of the most commonly used machine learning algorithms that you can consider using for your model. My typical approach here is to choose a few different models that I think might work well with my data and then compare their baseline performance using cross-validation. What I mean by this is take the standard implementation with the default hyperparameter values and compare the performance of the models using k-fold cross-validation with my training set. Then I pick the top 1 or 2 performers, depending on how many outshine the rest, and I will work to optimize those 1 or 2 top models.
You want to be on top?
Step 4 is model optimization. And this optimization is done using our validation set. The 2 main components in model optimization are hyperparameter tuning and feature selection. Hyperparameters, what a word! Hyperparameters are fixed values that you define in your machine learning algorithm that will determine the way that it learns from the data. This is where it's very important to understand the machine learning theory behind how these algorithms work, because expertise will help you optimize the hyperparameters. There are tools like grid search, which is built in Python scikit-learn library, that will try out different combinations of hyperparameter values to help you find the optimal set. But it would be impossible for grid search to try every single combination. It would take forever, probably an impossible amount of time. Like, you would run out of time, your computer would die before you tried every possible combination. So you need to have some expertise to know which range of values to specify for grid search to try out and produce the cutest model. All right, so second part of model optimization is feature selection. And feature selection is important because sometimes with machine learning, like with many other things in life, less is more. Some features may provide super valuable information to your model. Other features may just give it noise. If there are features in your data set that have nothing to do with your target variable and they're just confusing the model, then we want to get rid of those guys. So this is where feature selection comes into play. There are many feature selection methods out there, but I typically stick with using the feature importances native to most scikit-learn implementations of machine learning models. So typically you would look at the feature importances of each feature and choose the top n important features. And this value n can also be optimized using hyperparameter optimization techniques like grid search or any others. Step 5, model evaluation. Model evaluation means deciding how well our model is performing. How good of a job did we do in building something to predict something else? Wow, I really have a way with words, don't I? Once our model is optimized, we test its performance using our final test set. So this is that holdout set that we left untouched and saved for the very end. It's the very end, guys. It's time to use it, so let's use it. So we have our optimized model. We're testing it on the test set. The key was that squeak? The key decision to make here is which performance metrics to use. There are many different performance metrics that you can use. First, it depends on if you're building a classification model or a regression model. So for classification, the main ones are accuracy, AUROC, We have precision, recall, F1 score, and many more. And then for regression, some of the main ones are the R-squared value, the mean squared error, root mean squared error, mean absolute error. So you have to know what your options are and then choose which metric is best for the particular problem that you're solving. In the case of classification, you might be drawn to evaluate your model based on accuracy. Accuracy is simply a measure of how many predictions we got correct. Sometimes this is a great metric to use, but other times it is not. Let's say we have a very imbalanced data set. And what this means is we have far more examples of one class than we do of the other class. So let's say we have 1,000 data points, 999 of them are positive and 1 is negative. So this happens in business problems like fraud. This happens in some epidemiology studies with diseases. It's a very common occurrence that we have an imbalanced data set. In a case like this, let's say we build a model that has no intelligence at all, and it just guesses that the specimen is negative every time. If it's guessing that it's negative every time, it will be 99% accurate because 999 of them will be negative. However, that doesn't mean it's good. It's just guessing. So 99% accuracy isn't a good test of how good this model is. For something like this, we would want to look at a score like recall on the positive class. And what recall is telling us is how many of the positive cases were we able to identify. All right, step 6, we're done our model, we've evaluated it, we have all the code ready for it. Now it's time to deploy it so that we could share it with the world. When you're done building your model, you can deploy it using tools like Flask, Heroku, or cloud platforms like GCP. This is a whole other can of worms, so I'm not going to get into model deployment in this video, but if you would like to see a video on it, drop me a comment. I will leave some links in the description though to help you get started on model deployment yourself. There's lots of great resources online. That is it, my friends. Thank you so much for tuning into this one. Let me know your thoughts and let me know what else you would like to see. If you found this video useful in any way, it would mean so much to me if you hit that like button and if you subscribe to my channel. So thanks again. I wish you love, luck, prosperity, and high-performing machine learning models in your future. And that's all, folks. Bye.